Good afternoon and welcome you. Today we are continuing our stress distribution part 2. In this part, we'll be discussing about a vertical stress distribution for different types. First, for a line loads, different shapes like a rectangular or square raft, circular raft, and the embankment load. Also, we'll be discussing about some numerical at the end. Okay, so let us start with the first type of load. So first is the vertical stress due to the line load. There are the two types we consider. First, the vertical stress is due to the infinite load, and second, the vertical stress due to the finite load. So let us start with the vertical stress with the due to the infinite line load. Infinite line load is nothing like a retaining wall. It may be few meters or maybe even the kilometers it runs. So let us say this is a stress transfer by the retaining wall. It can be parallel to the any axis. Let us say here it is parallel to the y-axis. It exerts a pressure of the Q, that is a kilonewton per meter, suppose. Okay, uniformly distributed load along its length, and at a depth z, okay, and radial distance r. Suppose this is the point, any point P, at which is a distance x, y, z. Okay, at this distance we require a vertical stress. Okay, so this is a uniformly distributed load. So again we have to use our Bosenick's theory, and Bosenick's theory is given for a point load. Therefore, let us consider a small strip here. As it is parallel to y, let us say width is the dy. So this uniformly distributed load for this small element, I will try to convert into a small vertical point load as a delta P is equal to Q into delta Y. It is a small portion converted into a point load, delta P Q into delta Y. So because of this small element and this small load, the stress developed is also very small. So therefore, using the Bosenick's theory, so here because of that delta P, the stress is delta sigma Z. Okay, and this is the Bosenick's equation, 3 by 2. It is P now replaced with delta P by 5, 1 upon Z square, and function of R by Z to the square and pi by 2. So substitute delta P as Q into delta Y, and simplifying this in terms of Z cube upon Z square R square 5 by 2. And now sigma Z, this is for a delta sigma Z, and now for entire length, which varies from minus infinity to plus infinity. So we integrate this delta sigma Z over its limit minus infinity to plus infinity. So substituting this value here, so in this you'll find 3 by 2, Q by 5, they are constant. Even Z is also a constant, Z cube upon Z square R square. This is substituted here. Okay, now as Q is symmetrical, this Q is symmetrical on the both side of this origin, so we can take it out as a 2 times of this integration. So 3 by 2 Q by 5, 2 times 0 to infinity, taking from origin. And now R is expanded as R is nothing but a x square plus y square. So therefore Z cube x square y square plus Z square 5 by 2 dy. Okay, so these two to get cancelled, even Z is taken at outside, and now it is 1 upon x square y square Z square. Here you will find the variable is a Z because load is parallel to the Z, and other two are the constant. You can see it is along the Y, other parameters are constant. So x and Z is constant, and you have to solve the integrations. Okay, I don't think you can see here, but I tried one small attempt. You can solve it and I'll write the final result. You can take it like a x square and z square as a constant. Yeah, let us say a square. So it is a square plus z square, and then you can substitute. Let us this y is equal to a into 10 m, suppose. Okay, a into 10 m, and again checking the its limits, and then substituting here again. So you'll find dy is equal to a 10 m, and therefore you can substitute as a x and z as a square, and y is a y square as a square 10 square m. Therefore a square is common. If you take out a square common, so it will cancel with this 2, so a to the power 5 will be outside. Okay, and here that dy will be a into 6 square m. So after substituting that, you get finally is the integration of one of this constant, again 1 upon a to the power 4 outside, and you will get the integration of it's nothing but the a 6 square 1 upon to the 6 cube m, which can be again a integration as a cos square cos cube m. So finally it is a integration, this convert into a cos cube m, and you can solve further the integration of cos cube m as here I try to show. I made a one small attempt. Cos cube m as a cos square m into cos m. Cos square m can be solved as 1 minus sin square m into cos m. Then again you can substitute, let us say u is equal to z into sin m. So therefore u the du is equal to cos m dm. So after substitution, and try to check the limits, but here is the problem that when you to substitute m is 0, u is equal to 0, but m is infinity, you don't get a determined value. Okay, so finally it is integration of 1 minus u square du, and when you solve the final result, you try to do yourself. Okay, final result you get it as a stress at a distance z, which is the r distance away, or x and y distance away, is 2q upon 5z, and is a function of r by z, this square and this total bracket square. So this is at a distance r. If I want exact stress exactly below the load, I can put r as 0 like this. So you can also substitute r 0, it is 2q by z. Okay, so with this the first part that is over. Now second line load we go through. This is it is due to the again a line load, but it is a finite length is now defined, that is equal to 2 times a. Okay, so just like for example it's a compound wall, or maybe a strip footing with a limited length. So these are some common examples. This may be rest at a certain distance below the ground level, and suppose q is the that is the stress transfer at the basement at foundation level. So the length is considered as 2a, and let us we require a stress at the center, exactly at the center here, and at a depth z. So if I join the edges, so I get the angle, total angle is theta. Okay, so this is the problem. Now here we consider a small element here again of a length dx, as it is along the x. We can take it to the any axis, y also. So small element I considered at a distance x. Okay, So I convert into a point load. Okay, so it's like a delta small delta q. And then already we have defined this relation, this equation, for a infinite load, which was 2q phi z 1 upon 1 plus r by z. Now same I can use, and I'll substitute this load here. So this q I'll replace as a small point load, and because of that, using the same equation, I get a small stress delta sigma z. So substituting as q into delta y here, which makes the angle beta, suppose, and again it is a function of a x as it is along the x, so it is x upon z square, and outside square is 2. And then again we solve for this, take out all the constants, 2q by phi z. Now again I can take it from 0 to a half 1 multiplied by twice, so integration I taken as just like earlier, 0 to a 2 times, and this dx upon 1 plus x by z square and whole square. Now solving this integration, this time it is a simple one, replacing that x by z in earlier as a tan beta, because you can see here x by z is a tan beta x upon z. So I shown here is a x by z is equal to tan beta. So x is equal to z tan beta. So if I substitute x is 0, then beta is 0. But if I substitute x is equal to a, the limits, okay, then so x by z is equal to a by z here, and then I get tan beta. But what is beta again here? Beta is nothing but the here you can put it as a by z in this form, which is equal to, you have to find out a beta. Okay, so substituting this as a, what is this beta is equal to a final angle, that is a theta by 2. So when a by z, you can see I drawn the figure here, you get theta by 2. So it is actually tan theta by 2. So tan inverse of a by z is nothing, a by z is nothing but a tan theta by 2. So finally it is theta by 2. So the limits are 0 to theta by 2. And now you see in the earlier one, this 2 and 2 it become 4. So therefore it is 4 times q upon phi z with the limit 0 to theta by 2. Okay, and now substituting dx is nothing but z sec square beta d beta. Okay, and substituting the 1 plus tan square beta, that is x by z, which was tan beta and its square and its whole square 2. Okay, so this z get cancelled, and then remaining part here it is square and it is 4, so it is 1 upon sec square beta, which become a cos square beta. Okay, cos square beta can be written as 1 plus cos 2 beta by 2, and outside is 4q by phi z. So you can integrate, that is theta plus 2 times of sin 2 beta. After integration, this 2 become 2, and here when you substitute, it is 5 by 2. So when I take out 2, so this also get cancelled. So here is also 2 sin 2 beta, so 2 is also get cancelled. So the final form is q by phi theta plus sin theta. So in this expression, this theta is in the radian, this can be in the degree. So the stress calculated at exactly the center of this finite line load at a depth z is x given in terms of a theta. This theta is nothing but this total angle subtended by the edges. So ignore the upper part. Now suppose I require the stress at any distance away from the center. So if I required away from the center, let us say this point N where sigma z is required, and it is at a distance x distance away from the edge. Okay, so joining these two corners, it makes an angle theta 1, and with vertical the angle is alpha. So the required point is away from the center. Again, the depth is constant. So first we'll find out this alpha. Even this is inside but away from the center, same figure is there. Alpha will be the inside. Okay, so alpha is x upon this x upon z. Okay, so that is tan inverse of x upon z, and again after solving we get sigma z as q by phi theta 1 plus sine of theta 1. Theta 1 is this, again angle subtended by the edges, sine theta 1 cos of theta 1 plus 2 times of cos alpha, 2 times of cos theta 1 plus 2 times of cos alpha, where this theta 1 is in radian. So this is how we completed the first two line load. First was the infinite, and second one is the finite line load. Now we'll go to the another shape of the loading, which is also very important in a okay. So vertical stress due to the circular load. So the various circular loads or their pressures are used in a practice, just like oil tanks or any tanks, naphtha tanks, circular footings, or the silos. But sigma z is used particularly for check the contact, to check the pressure at different depth, and also for the settlement. Okay, so consider a circular load with a radius a. So outer radius is a. Okay, and intensity is q. This is in a plan. You can see outer one is the radius a and intensity is q, and we required stress at a exactly center at a depth z. Okay, now to analyze this, let us consider a small ring inside, as shown in the green color, at a radius r, and its thickness is dr. This is a ring at a radius r, intermediate ring, and its width we can say, not thickness, dr. So the area of this ring will be a twice pi r dr, area of this ring, and intensity is q. When I multiply with the intensity, then I get a small equivalent to a vertical point load, that is q into the area, that is 2 pi dr r dr into q. Now using the Boseniuk equation, this p can be substituted delta q. Therefore the stress developed is also for the ring is delta sigma z. So substituting this p from here and simplify expression is this, is in form of z cube upon z square r square phi by 2, and integrating this, when I integrate our maximum radius r is equal to 0 to r is equal to a, so integrating from 0 to a this expression, so taking out all the constants outside, so you'll find 3q zq, that is also constant depth. So variable is r, that is a radius. Okay, inside this r is a variable, z is a constant. Okay, so by substitution, z square r square is equal to say n square. So then we can write this 2r dr is equal to 2n dn. Therefore r dr is equal to n dn. So r dr can be substituted as a n dn, and the limits, when r is 0, then n is also equal to z. R is equal to 0, n is equal to z. When r is equal to a, then it is z square a square and square root. So n is equal to z square plus a square into square root. So these are the limits 0 to z square a square. R dr is n dn, and z square r square is replaced as a n square power 5 by 2. So finally it becomes a n to the power minus 4. After integration, it will be minus 4 plus 1, minus 4 plus 1 with these limits. And then after solving this integrations here and then substituting with these limits, finally we arrive with a simple expression. You'll find it is a Q intensity, and then 1 minus this bracket power 3 by 2, where it depends upon the A by Z. A is the maximum radius. Sometimes we also call as a maximum radius R. R1, R2 like this, maximum radius of the footing or a tank. So you'll find that this is also something like an influence factor, and sigma Z is the KBC. Earlier also we found that there was an influence factor for a line load, and from the influence factor we can draw a pressure distribution just like a point load. You can draw at a different constant depth uniform distribution on horizontal plane. Similarly, at a constant radial distance r, you can draw a vertical distribution. Okay, so and also you can draw a isobar by using this influence factor, as we have discussed earlier in the horizontal distribution, vertical distribution, and isobar. The procedure is same. Now let us first go through some numerical on the first two part. The first numerical is on the the loads, that is the first infinite load. Okay, so let us say 500 meter long is a big length retaining, so that's why we consider it is an infinite length as a practical problem. Retaining wall running parallel to each other, and their center to center distance is 3 meter. The corresponding loads are the load intensity I showed here. These are two retaining walls. They are running 500 meters. Their intensity is first is 25 kilonewton first retaining wall. Second retaining wall is a 50 kilonewton per meter. So these walls rest at a sandy stratum of a 10 meter depth. Total depth is 10 meter depth. And their foundation is taken as a 2 meters. So plot the horizontal distribution at the center of the sandy stratum. Center of this means total is 10. So center of the stratum is 5 meter at 5 meter. Both the retaining walls are founded at 2 meter below, so 2 meter below. So therefore, the clear distance between their foundation and horizontal, the required plane, is 3 meter. Center is 5 meter, 2 meter is foundation, so remaining is the 3 meter. So our Z is the 3 meter. Okay. So what we'll do here, we know this is the expression as we defined for an infinite load. Here two walls are shown. Okay, to draw a distribution we need to take some coordinate. So let us consider this as a first retaining wall. So here it is 0. On left hand side I take some coordinate, let's say -1, -2, they may be in meter. Right hand side I can take 1, 2, 3. The clear distance is 3 meter. Beyond this also I can take 4, 5. You can take more also. Okay, so considering first retaining wall as at 0, 0, we for the purpose will neglect this wall because we are using a principle of superposition. Then second time we'll consider this wall and we'll neglect this wall. When you consider this wall, we'll consider this as a 0, just like this. Then these two become -1, then -2, -3, -4, -5. Where on right hand side it will be 1, 2. Coordinate system will be accordingly changed, just like the first. Here I shown the coordinate system when we consider the first wall. Similarly, we can write the coordinate system second wall. Okay, so here I prepare a table. The first part of the table when we consider the first wall, neglecting this. Second part of the table we consider the second wall, neglecting the first. So first retaining wall, the load is all 25 kilonewton per meter. The depth is required is 3 meter. Now from this you take a radial distances. First one is the maximum is -2, -1, -2, -1, 0. They are here. 1, 2, 3, 4, 5, up to 5. One can take even more coordinates also. So then find out this R by Z. Okay, first two are on the left hand side, there are minus, others are plus. Then you substituting this expression, you can find out sigma Z. So this is the first part. Now considering the second wall and neglecting the first wall, considering this as 0, -1, -2, -3, -4, -5, and right hand side it is 1, 2. So you can see here -5 minus, so maximum is -5, -4, -3, -2, -1, 0, 1 and 2. So find out their R by Z. Z I put it here the same column, 3 meter. So R by Z. So up to 0, left hand side of the wall all are the negative and right hand side of wall are the positive. So substituting this equation you can find out sigma Z. And now you add this sigma Z for 50 kilonewton per meter and this sigma Z for 25 kilonewton per meter. Principle of superposition, you get a total. That is the stress developed on this horizontal constant depth with varying R. You can plot it also, so I can show you here. Yeah, this the plotting is shown here. You can see here 2 points and how it varies. Its maximum here and decreases. Okay. Now we'll take another problem, that is on the finite length. So here the determine the stress due to the compound wall 4 meter in length. Now the length is limited, 4 meter length, and resting on a matrix soil, maybe say muram soil, at 1 meter below the ground level. So their foundation is resting 1 meter below. Okay, and you have to find out the stress at 6 meter. Okay, at horizontal plane. Okay, so determine the stress at the center of the compound wall. So the first part is you have to determine the stress at the center of the compound wall and then 3 meter away from the corner of the wall. In two cases we have to find out this. The uniform stress transferred by this wall is 50 kilonewton per meter. Then here the problem is drawn. So total length, this 2A is a 4 meter. Okay, and the 1 meter, it is 1 meter below ground level. Total depth is 6 meter. Therefore clear distance is Z is 5 meter. So we have to find out with the Z as 5 meter. The first case at A, at the center, it makes angle theta. Second case, it is 3 meter away from the edge. Okay, so in this case this will be theta 1 and this will be alpha. So the first at the center of the this load, this compound wall. So the expression is q by phi theta sin theta, where theta is this subtended by the edges. So first you find out this theta. So when I take tan of theta by 2, it will be A upon Z. Therefore I require total theta, so I multiplied by 2 times tan. Okay, tan inverse of theta by 2 multiplied by 2, so I get the angle theta. Okay, so substituting the values here, total A is now total is 4, so A is 2 meter, and here you can see 4 by 2, and depth is the 5 Z meter, so you get angle 43 degree, or in radian 0.761, because first theta we required in the radian, so substitute here in the radian, and sine of this angle multiplied by the intensity is given 50 kilonewton per meter, so total value is 23.088 kilopascal. This is the first part. Now second part, we require now a stress at a point B, which is away from the corner at 3 meter away. Okay, so expression is given by at B theta 1 sin theta 1 cos of theta 1 plus 2 alpha. So first calculate alpha, this alpha, that is this x by z. So tan inverse of this. So therefore substituting value x is 3, z is 5 meter. So you get 0.291 radian or 30.96 degree. Then theta 1 directly cannot be obtained, so therefore we take combine theta 1 plus alpha. Theta 1 plus alpha. So total distance will be 4 plus 3 7 by z. So tan inverse of 2a plus x by z, that is 54.46. Okay, so therefore from this total subtract the alpha, so you get the theta 1 as 23.50 or 0.41 radian. Now substituting this theta 1 as 0.43, first is the radian, then sine theta 1, that is in degree, then cos of theta 1 in degree, okay, plus 2 times of the alpha value. After substitution we get a total stress of 7.03. Okay. Now we'll solve a rather numerical for a circular flow. So let us take a silo which is supported. Silo is a structure which is having like a big tank, and it has huge diameter and big height to store the different materials. Okay, and how is the foundation? It is resting, or even the tanks also, it is resting on a beam. They call it the ring beam. It is foundation is called as the ring beam foundation, that is the RCC beam. Okay, nearly at is the edge, so entire tank is resting on that. Middle portion is not directly touching, but middle portion is filled with a granular material, that is called as a ring foundation. So a silo is supported on a ring foundation whose outer and inner radii are 7 and 5 meter respectively. Total load is 5000 because it is a huge 5000 kilometer is transferred on this ring foundation. Determine the stress at 10 meter below the foundation level, not ground level, directly mentioned. Also draw the vertical stress diagram up to 10 meters. Okay, so a total 10 meter thickness is given, and total load is given 5000. So this is a ring foundation. Outer radius is 7 meter, inner radius is a 5 meter. This is the silo is resting on this ring foundation, and ring foundation is, you can see here, is resting on this foundation level. So it is transferring the stress along the ring. So first find out this area of this ring. So cross section area of the ring, pi r square, that is two different radius, 7 square minus 5 square. So area of this ring is 75.40 meters square. So find out of how much contact pressure is transferred. Load upon area, load is 5000 upon this area, so we get the stress 6.31. so that is the stress transfer on this foundation level. Now using the equation which we had derived earlier for a circular circular load, the function of this q and function of this a by z. A is nothing but these are the radius, maximum radius, outer and inner. So what we'll do here, again use the principle of superposition. First we'll consider the outer edge, and suppose that entire area is loaded, we'll find out the sigma z. Then we consider the inner edge, considering that inner edge is subjected to the entire stress, we'll find out the sigma z, and subtracting these two sigma z, so like this we get a q value, sigma z value as as q is constant, so therefore is a difference of basically the influence factor. In both the case, this cube remains same, only this part changes as the radius changes. So we'll find out the influence factor for the outer radius and influence factor for the inner radius. So you can see first in a tabulatric form, these are the Z. You can take any interval. You can take even the 1 meter also, 0.5 meter also. The depth total is asked is 10 meter. Now radius first is the outer. First table is for outer. Second table is for the inner. So outer one is a 7 meter. Okay, Z is given. So find out R by Z values and substitute in this expression. So we get first influence factor for the outer radius, this one. Then for the inner one, radius is 5 meter. Then again Z is common here. So R2 by Z values. Again substituting the equation, you get the KB value for the second radius. Okay, so subtraction of these two, you get finally the net values. With respect to Z, we get the net value, and when you multiply it by the Q, you get a distribution. I have shown here in this Z versus the sigma Z values. So therefore, these are plotted here along the vertical axis. We require a vertical distribution which is asked here. So you'll find that it is increasing up to this and then decreases. So somewhere it is increased maximum. We can find out that distance and that angle be also as a similar one as we discussed in the point load. Okay, so this is how the problem which we solve for a circular load. Okay, so we cover the total 3 problems. First one infinite load, second is finite load, and then circular load. Now we'll move to the another shape. Again the important shape of the foundation. So uniformly loaded rectangular area. Many times we use a raft in that may be on the basement or the surface, mostly in the basement. Okay, and that raft transfers the stress. The columns are taken received by this raft, and total load is transferred on the raft. And at the bottom of the raft, let us say this is a rectangular raft. Length is L and this width is B. It transfers the load Q after total load calculations. Okay, and that level, suppose it may be a basement level, X indicate maybe a basement level which may be below the ground level. Now in this case we'll derive the expression of to find out vertical stress at a corner instead of center. There is also equation at the center, but we'll find out first at a corner. So it is a simple expression, that's why it is taken at the corner, which is at a depth Z. So along the x-axis it is a length L, along the y-axis it is the width B. So I consider a small element here at the center. If I draw one strip here, if I draw second strip here, so interaction of these two strips gives you the along the x small element dx and the dy. Okay, so this element is subjected to the same stress, suppose Q, then I can convert into a load of a small load. So using the Bosniak's equation, the basic equation, now consider this element and the load, small point load, because we require a point load here, as Q is the intensity multiplied by this area. So I get a small load here. Because of that load, the stress developed at Z is the delta sigma Z, because we are considering the element here. Okay, so replace this Q with this delta Q, Q dx dy. Simplify this, Z cube, Z square, x square, r square. R is replaced by x square plus y square. And now integrating this equation, now here in the two length, first integration over r is equal to along the length 0. So this is the origin now, 0 to L and 0 to B. So you get a two or double integrations here. First for the say length or width, second for the length. So we can write this as a expression, integration in this form, and it is a big expression, not so simple to derive. It can be. Okay, so the whatever the result we get, it is in terms of the stress transfer, that is the at a rough level, into that influence factor. R I put it just to indicate for the rectangular footing. So this in the final result, this influence factor expression can be written in the big form. You'll find there are the M and N, where what is M? It is L by Z, length upon Z, and what is N? B by Z. Then if you using this two dimensionless factor, the expression is derived. You'll find that in this expression 2mn m square n square 1, this is sometimes this part is common. You can find here it is common, here it is also common. In the denominator m square n square 1, it is also same, it is here, only the plus become a minus. So this term is multiplied by this m square n square 2 and m square n square plus 1, plus after multiplication this plus this 2mn, again it is the same, this term is same, means this bracket you will find it is almost repeated, except instead of plus it is a minus. So only this term is a slightly different. So this KBC, all these terms can be the values can be written by substituting different values of n for a given value of n. So you can see I can take a interval here, let us say 0.1, 0.2, 0.3, 0.4. The values are available up to 6, or one can calculate also. For a first value of 0.1, I can vary the value of n even up to 6 or more, and I can write all this. For example, I given the first values only. So you can even avoid this expression because too lengthy sometimes. So you can select this KBR directly from a table, okay, multiplied by Q, you get directly the stress at different level. Okay, so let us solve a simple problem based on this. Determine the vertical stress at the center of a raft 4x4, which is square, and at a depth 4 meter below the basement level. Suppose this is a raft at a basement level 4x4 meter, and it applies the stress of 200 kilopascal, and we require at the center, okay, and depth 4 meter. Now the sigma z equation which we discussed is at the corner, but here we required at the center. Therefore, for our convenience, what we'll do, we'll take this center to form as a corner, so that our purpose will solve, because the equation which we are written is for the corner. So how we do this raft, we can distribute it into the 4 part, okay, and as a principle of superposition we can add all this. So if you take a first part, second part, third part, fourth part, center of this is the required point, and you will find the corner of suppose 1, as shown in the sample. For a 1, this point at center point, it become a corner here. For 2, this again it is a corner. For 3, it is a corner. For 4, it is a corner. Okay, so it means we can take a one element, one part out of 4 and solve that. Okay, find out the KBC for that one part, and you multiply it into the 4 parts. The principle of superposition. So you get to do sigma z as 4 parts Q into the K value. Okay, so using that expression, what is M? Now we are considering a one part. Now total length is 4, therefore here for this one part is a length 2 by 2, and depth we required is the 4. So M L by Z and N B by Z, both values are 0.5. Substituting in this expression, calculating carefully, This part is in radian. You have to remember that we are putting in a, because a tan, this part I put it in a radian. Okay, so after substituting we get it is a 0.840. Suppose I refer a table, I also get the 0.5 and 0.5 value, m and n also get the same value. So 4 times that stress 200 into 0.840, I get 67.2. So that is how a stress is calculated for a, it is called as a plate or a the raft. I will take another problem where there is a combination of the two loads. Determine the vertical stress due to the composite area as shown in the below. Take the contact pressure is 150 kilopascal. Okay, so you can see here in a plan the load is given. It's just like a raft. Suppose one side it looks like a rectangle plus semicircle, and we require the stress at a point, that is exactly center of this semicircle or center of this. In a cross section it exerts a pressure of 150 kilopascal, and here you have to find out this at a depth which is mentioned somewhere, at a depth 3 meters below the we required to find out sigma z at 3. Here it is 3 meter exactly below a, the ground level. Okay, so as we know that our expression is for a corner, so what we'll do, we draw a line from a in this rectangle area and divide it into this rectangle into two parts, part 1, part 2. So the a point will be the corner for each. At the same time, this is the circular part, okay, half, that is semicircle, and a part it acts as the center because we have expression for a circular area at center, whereas rectangular area we have expression at the corner. So finally sigma z is equal to q times kbr for first, kbr for second, into kbc for circular. First two are their geometry is same, so therefore I can take it as 2 times of this influence factor for the rectangle and influence factor for this. Of course this will be the half. So using the expression or a table, first find out n, l by z. L is 8 meter and z is 3 meter. So you can find out this, you can find out n. Okay, so you get m is 2.667 and n is 0.5. Okay, because it is 1.5 and depth required is 3 meter. Okay, so you can use a table or expression, you will get the influence factor. First for this rectangular is 0.1365, this is for one part. Okay, now for a this semicircular part, so I written here is the half because we have expression for a circle. Okay, so again it is function of r by z. Now here r is the radius 1.5. Okay, so please check the calculation again. So after substituting this we get 21.9 kilopascal here for the this one, that is for circular. I calculated separately. So for a rectangular area, q is 150, 2 times of influence factor 0.1365 plus directly I added here for a circular. So total is 62.26. So this is how we get a stress for a combination of the loading. Here the required thing is that the load can be divided into a geometry for which we have the expressions. Now we'll go for the last type of a loading, which is another important loading. Many times we required in the road work, that is the embankment loading. Let us say this is the embankment in a cross section, and it has a height h. Okay, top width is this, and this is the bottom width. The side slopes are given, the 1:2 one vertical is to suppose x horizontal, and the embankment is compacted with a required density. We generally follow our standards like a MDD and OMC, like that. So after that we get, suppose this is compacted, and compacted unit weight is a gamma. Therefore the uniform stress transfer here, okay, we consider this as a maximum part, okay, and that we consider as a uniform, okay, though it is a tapered here, we consider as a uniform stress transfer, which is gamma into h, unit weight into the height of membrane. Okay, now here suppose we required a stress at a point n, which is at a depth z, exactly center of this the embankment. So you join this outer part, join this the edge of the top width. So this makes an angle alpha 1, and this makes an angle alpha 2. So outer distance is a. Generally, how do we calculate a? From this 1 is to 1 vertical to xh. So if I multiply h into this slope component, horizontal component, I get a value. For example, if it is a 1 is to 2 and height is suppose 3 meter, then 3 into 2 6, a becomes 6. B, here to be confirmed that it is a half. Actually we required the half portion of this embankment. Okay, B is not a total width, it is half of the top width. Okay, so first we'll calculate these angles alpha 1, alpha 2. So first calculate this total. Tan inverse of this total means a plus b by z, and alpha 2 is equal to tan inverse of b by z. So subtract this from this, you get alpha 1 also. So we have two formats here, either you remember first or second. The first one, 2q by phi a in a bracket a, and angle alpha 1 plus alpha 2 plus b times of alpha 1, or 2q upon phi a plus b by a in bracket multiplied by total angle alpha 1 plus alpha 2 minus b by a alpha 2. Any one form can be used. Okay, we'll see again a simple example on this embankment loading. So consider the embankment load of total width is 4 meter. So determine us the vertical stress at 4 meter from the top width, or a height of embankment is 3.5 with a slope, side slope is 1 is to 2. The embankment is compacted with a unit weight of 19 kilonewton per meter cube, and the stress is required at 5 meter exactly below the ground level at the center. So you draw the figure. So top width is given 4, means our b value is half, that is 2 meter, and height is given as 3.5 and 1 is to 2. So 3.5 into 2, it becomes 7. So a value is 7, b value is half of 4, that is 2. A is 7, b is 2. Okay, so first you calculate these angles. Let us say this is alpha 1 and alpha 2, alpha 1 plus alpha 2, a plus b by z. So you get 1.064 radian. Here most important thing that all these values, alpha and alpha values, are in the radians. Okay, alpha 1 or alpha 2. So so calculate alpha 2, that is this 2 by z, substituting b as this 2 and z as 5, you get 0.381, and then subtracting this from this, you get alpha 1 also 0.683. So q is equal to gamma z, 19 into height of embankment 3.5, that is 66.5 kilopascal. After substituting the expression, you will get total stress is 53.3, that is at the center. Here equation is not still available for any distance away from this. So you get only the distribution exactly at the center, which is the maximum. Okay, so in this way we cover the different shapes. Okay, we started with a line load, and then the different shapes like a circular and rectangular and embankment loads. Okay, and we solve numerical. The next time we'll see when the suppose load is a irregular shape, not is a regular shape. Different options, because in practice you'll find a raft is not necessary to be say a circular or rectangular or square. Sometimes it has offsets, okay, complex type. Then these expressions are not useful. Okay, so therefore a new mark is the person who has developed a chart for all types of, even in the regular also we can solve, but most useful for a irregular shape of, okay, uh, load. And even it can be obtained at a different distance in a plan, with not necessary to be center, corner, or away from that, you can find out. Okay, so with this we finish this. I'll forward one simple question for you, try to solve and send it to me as usual. Thank you.